Well, I've made all the mistakes that a man can make in the stock market except to go broke. You have to foresee the future with a high degree of probability of being correct, and then you have success in your hand. But we'll not go into that subject. I haven't looked at the stock market for about 2 months as I worried about this talk. When I was verbally asked to be on this program, I was told that a summary of research I did was not wanted. What was wanted was how my brain functioned as a research man and how structures research came into being here at Langley Field. We Americans are a people with different backgrounds. I was born on a farm in northeast Nebraska. I recall our move to a small town when 2½ years old. I attended the first 6 grades in the village school, where one teacher taught 2 grades, and where the most revered and highly respected teacher flogged the bad boys herself instead of sending them to the principal. My brother, 10 years older than I, was the model boy that I wanted to be like. He was always honest, kind, helpful, patient, and did not do the unkind things that other boys sometimes do. The continuously happy part of my life began in May of 1918. My older brother was in the Army. My father could find nobody to work the farm, so our family moved from a modern house with electricity and indoor plumbing to the farm where these did not exist. Every day I worked with my father, doing a man's work as best a 10-year-old boy could. My father gave me my first lesson in research. One day he said, "We will use the shovel cultivators for the first half day, then change to the disc cultivators and see which gives us the larger harvest of corn." We learned that the disc cultivators was the better. My father was an observing man. He would look somewhere and say, "Do you see what I see?" Of course I did not. He would then tell me what he saw and his interpretation of what he saw. Once in the spring of 1919, he observed a field that had been in corn the year before. He pointed out alternate strips of grass and no grass, that he had cultivated where there was no grass, I where there was grass. He said that I, 10 years old, was not strong enough to push the shovels of the cultivator in deep and destroy the grass. I took my 7th and 8th grades in a rural one-room school where one teacher taught all 8 grades. At times it was 20 below zero as we older pupils helped her build the fire. There I enjoyed arithmetic and geography. As I look back on my life, I see where curiosity and a desire for understanding are essential qualities that a research man should have, in addition to honesty, patience, and a willingness to work long and hard. My first strong desire to learn came during the influenza epidemic of 1918. Schools were closed. We had over 2,000 lambs that had been purchased from the western ranges. One lamb had a long tail. All others had short tails. My younger brother and I were fascinated by that lamb with the long tail. We would talk about it, always look for it, catch it, hug it. That lamb was our favorite. One Sunday afternoon, my father called to my younger brother and me, "Come here, I'll show you what happens to the lamb's tails." He had found a book that my older brother had brought back from college. It showed a lamb's tail being cut off and told why. I was fascinated by that book. I read it many times. When I saw a sick lamb, I would tell my father what to do. We set up a sheep hospital. About half of the sick sheep recovered, so our death loss was cut in half. That book also told how to prevent lambs from getting sick. So we reduced the hospital admissions. My interest in the farm animals became so great that I also studied books on cattle and hogs. One day a cow was so bloated that my father hesitated to milk it. He was afraid it would fall on him. The cow was in such misery. I showed him where to punch a hole to let the gas in the stomach escape. With a butcher knife, he was able to relieve the gas pressure and the cow lived. By the time I had finished the 8th grade, I knew it all. I was not going to high school. I told all my relatives in the presence of my father that I was not going to high school. My father said nothing. On the morning to start school, my father finished his breakfast, then said, "Eugene, go and get ready to go to school." I did as father directed. My father had had very little formal schooling, but he realized the importance of it. Having an intense interest in agriculture, half of my first 2 years in high school was devoted to the study of agriculture. In addition, I studied algebra and English in the first year, plane geometry and English the second year. I enjoyed plane geometry very much. In the summer between my second and third year of high school, I took sick. Not sick enough to be taken to a doctor, but lacking in strength so much that I could not work on the farm. So I read books that my older brother had brought home from college. One was on agricultural engineering. What I read in that book, plus my fascination with plane geometry, and also the high truss bridge across the Missouri River at Sioux City, Iowa, a city that we often visited, caused me to decide to be an engineer and build bridges. I was not sure I could trust the principal of the high school when he said my agricultural courses would satisfy science requirements for entrance to the university. To me, agriculture was the everyday farm work. So I took extra courses during my last 2 years in high school to be sure I would be admitted to the university. At college, I studied civil engineering. My special interest was structures. I asked my structures professor if I should continue graduate study. He recommended against it and suggested I go to the American Bridge Company for a year or two making detailed drawings. He said that if I got too much knowledge, I would find others working beside me would not appreciate my better training, and I would get discouraged and end up back at a university teaching like he did. I had not been at the American Bridge Company at Gary, Indiana, more than a few months when I knew I had studied the wrong thing. I should have studied airplanes. Every night as I lay in bed, I would see the lights on the mail planes as they flew around the southern end of Lake Michigan. They will never build a bridge across Lake Michigan, but they will fly across, I thought. Airplanes are a bridge of a different kind. At work, I saw men with 5 and more years' experience doing the same sort of work I did. Although I asked for the more unusual jobs and was given them, I was glad when a stroke of luck came my way. The National Advisory Committee for Aeronautics offered me employment as a result of my having taken civil service examinations when in college. I answered, "If you think it is all right to employ me, knowing that I know nothing about airplanes, I know that I will succeed because I will study at night and teach myself." When I came to Langley Field in March 1929, I learned that aeronautical research consisted of measuring the pressures caused by air flowing over airfoil sections. It was being done in every wind tunnel. I was assigned to measure air pressures generated on wings and the fuselage of an airplane in flight. I was told that the purpose of all this work was to learn what forces should be used to design the airplane structure. For my first 6 months, I read film records and made pressure plots of air pressures on the wings and fuselage of an airplane. When my supervisor handed me a letter that raised my pay from $2,000 to $2,200 per year, I told him I thought it was more important to think about the significance of what we were doing than just keep on plotting pressures. He said it was all right to think some, but don't let it become obvious. Or everyone in the office will want to stop working and start thinking. When I came to Langley Field in March 1929, I had started reading books on the aerodynamics of the airplane. To me, loops, rolls, dogfights produce structural loading on the airplane comparable to moving loads on a bridge. Therefore, I kept asking myself a question. What is it that can do for the airplane structure what influence lines do for bridge structures? One day in the spring of 1930, the answer to that question came to me suddenly. I was reading a thesis by Jimmy Doolittle. He had one sentence so well written with such a clear meaning that I could write other sentences like his sentence, with each sentence describing a curve on a chart. The ordinate is the lift on the airplane divided by its weight. The abscissa is airspeed. The top curve is the Doolittle curve for C sub L max. It represents the distribution of forces on the airplane at maximum lift. The other curves are for lesser lift coefficients, all the way down to negative C sub L max for upside down flight. The curve for each lift coefficient represents a different distribution of forces on the airplane. As the airplane flies, it explores an area on the VG chart. The largest force for each distribution of forces represented by the curves will be at the perimeter of the area that is traced out during the life of the airplane. So with a knowledge of what the airplane is desired to do during its life, a decision can be made as to where the perimeter of the VG diagram should lie, and then design the airplane to be strong enough to withstand the forces defined by that perimeter. I had explained these ideas to my supervisor, but he would not only listen and say nothing. In the summer of 1930, Lieutenant R.D. McCart, who had been assigned the job of being responsible for the strength of all naval airplanes, visited Langley Field. I was assigned to talk with him because my supervisor was not there. I explained these VG ideas to McCart and told him I would send them to him in writing through official channels. The next day I told my supervisor what I had promised McCart, and again explained my ideas to him. This time he asked, "How does this solve the air bump problem?" In no more than 5 minutes, on a piece of paper no larger than an envelope, I derived the simple formula for how much the lift on an airplane is increased when it encounters an upcurrent of air with a velocity u. I completed my memorandum on the VG diagram for airplane design. When I learned that it would not be transmitted to McCart through official channels, I put it in an envelope with a 2-cent stamp and mailed it to him. McCart recognized the merit of the VG diagram and had the Secretary of the Navy ask the NACA to keep these ideas secret. Then McCart required all naval airplanes to be designed to the perimeter of VG diagrams. The Army Air Force quickly followed suit. I might say that Commander McCart and I were close friends until the day he died. When the pilots here at Langley were informed of our desire to test the formula for air bumps in flight, they told us that a bump could always be found over the bridge between Fox Hill and Grand View. On a warm summer day, Mel Goff and I flew over that spot at different airspeeds, and the upcurrent of air was calculated from the bump acceleration recorded on the airplane. Except for one pass over the bridge, the calculated velocity of the upcurrent of air causing the bump was the same. These two ideas concerning VG diagrams and air bumps completely changed the direction of research in the office where I worked, and we finally stopped the plotting of air pressure curves. Also at about this time, the idea of replacing the fabric covering on wings and the fuselages with a thin sheet of metal began to be considered. I was therefore asked to make a study of the literature on this subject. Because there was a dearth of literature on this subject as applied to airplanes, I talked with naval architects who build ships with metal plates for the outer covering. Among my contacts with naval architects was Henry Bengtsson, a research-minded man born in Sweden who studied naval architecture in Germany during the 1920s and was the expert on hull strength at the Newport News shipyard. He was the first person to introduce me to problems encountered in building metal shell structures. We became close friends, and in the years that followed, both he and we in structures research at Langley benefited from the work of the other. His design of the foundations for gun turrets on warships was based upon structures research we did here at Langley Field. I continued to study the literature from which ideas for research papers formed in my mind. I found that the writings of S. Timoshenko were a great help. My goal eventually was to write my papers so well that Timoshenko would take note of them. He was the man I wanted to be like. I was so glad when I met him, as I did several times, to learn that he had a kind and gentle personality, like my older brother, who I so admired and wanted to be like. In 1931, Paul Kuhn came to work in the same office where I worked. He joined in the study of all metal airplane structures and began writing papers. In the early summer of 1938, I learned that the civil aeronautics engineers believed that much more structures research should be done at Langley Field. They liked what Paul Kuhn and I were doing. So I planned with them a course of action that would greatly increase structures research at Langley Field, but it would require a change in basic policy of the NACA. When I informed Dr. Lewis, the director of research in Washington, what I had done, he said, "I have talked with you more about NACA policy than with any other employee. I don't know whether that was a mistake or not. You may have started something that should be stopped and can't be stopped. If that is the case, you are finished at the NACA. We will have to wait and see what happens." Well, in the morning, when the committee was to meet to make the decisions, Dr. Lewis said, "Now the chairman will sit here. I'll sit next to the chairman and you sit next to me so I can kick you under the table if it's necessary." The meeting opened like the civil aeronautics people and I had planned. The civil aeronautics man made a motion to set aside the entire order of business, that the great increase in structures research at Langley Field was the only thing of importance to talk about. And then he put a question to me. All morning long, I spoke for the NACA and began to get hot under the collar. I still had not been kicked. Finally, at the end of the day, it was settled that there should be a $1 million appropriation asked for a structures research laboratory. And as I went to go home that evening, Dr. Lewis said, "I didn't find it necessary to supplement anything you said. You handled yourself so well." So I felt much better than I did after the previous conversation. The structures papers that Paul Kuhn and I had been writing always dealt with a clearly defined but often idealized problem which we set out to solve. So in the planning of the Structures Research Laboratory, we retained these ideas. We deliberately did not equip the laboratory for the static testing of finished airplanes. I feared that if we equipped ourselves to static test the structure of complete airplanes, such work would crowd out the more basic structures research that we felt was needed. The Army Air Force, Naval Aircraft Factory, and airplane companies were doing this kind of work already. As the Structures Laboratory building neared completion, I was placed in charge. The personnel department began sending us engineers just out of college. When their number had grown to near 20, we had a problem. Paul Kuhn could write a paper I thought was fit to publish. I could write a paper Paul Kuhn thought was fit to publish. Nobody else seemed able to write a paper that either Paul or I thought was fit to publish. To solve this problem, I wrote letters to deans of engineering and heads of civil engineering in colleges describing the kind of man I wanted to employ. The first man so obtained increased our productivity 50% or more. We used Evan Schutte to help others organize their work and write the papers. One day, Elton Miller, the chief of research here at Langley, brought me personnel papers where Dr. S.B. Batdorf, a physicist, sought employment with the NACA. Nobody, either at the Ames laboratory at Langley, had a place for him. His question to me was, could Dr. Batdorf be useful in structures research? I had not read more than 2 paragraphs until it was clear this man Batdorf had brains, and he knew he had brains. So I said, yes, we can use him. I was receiving no technical guidance from men in authority over me in the NACA. I must have men working under me who are more able than I, or I cannot carry ever-increasing responsibility. I could not forever rely on my friends in the Bureau of Standards and the Navy Department for help and guidance. Dr. Batdorf loved a mental wrestling match. I gave him a problem to help me straighten out my thinking. He straightened me out so quickly that I said to Paul Kuhn, let's give this man Batdorf the toughest problem we can find and give him a time limit by which he shall solve it, and I'll bet he comes through. Paul Kuhn selected the problem. We each told him everything we could to help him understand the problem. Then we said, use 2 months to familiarize yourself with the literature and the nature of the problem, and then have it solved 4 months from now. In 2 months, Batdorf had cracked the nut in that problem to where Paul Kuhn said, I can now finish it, and Batdorf went to work on another problem. I once had set a time limit of 23 calendar days for myself to solve a problem and write a report. I found that I had correctly judged my ability. So once I asked John Hobolt if he would accept the challenge, solve a problem and write a paper for oral delivery in 20 working days. He accepted the challenge and proved that both he and I had correctly judged his ability. Another time, Dr. Batdorf and I asked John Duberg and Bernard Budiansky to sit down together and solve a problem in a small fraction of 1 day. They also proved our estimate of their ability was correct. We never asked any man to do a research job without also giving him all the help we could. With each job done, a man grows. We wanted men to grow fast. Often management asked that something be done, and an estimate of the time required to do the job was then made. Paul Kuhn, then we would not start until that amount of time remained. Paul Kuhn would object. He thought we should start sooner. When he discovered himself that management above us changed their mind so often, he finally agreed that my policy was best. We wasted less time. Dr. Batdorf had studied under J. Robert Oppenheimer of atomic bomb fame at the University of California in the field of quantum mechanics and cosmic rays. He also had special training in mathematical methods. At his suggestion, he began giving lectures to us in structures research to aid the education of all of us. When I saw how well men developed under his influence, I gave much thought to how new men at the lowest entrance grade could best be given a start in structures research. By chance, one of our men, who was quiet, patient, and kind, with a soft voice, and was developing to be a very good research man himself, told me how he could tell in a few days whether a new man had promise of becoming a good research man. After that, I assigned each new man to start with him. He would then help me decide where to place the new man if we kept him. If the supervisor of a new man later on ever failed to give him the help he needed, the new man could always go to Charlie LeBeau for help. When I made the decision that every new man should be started right, I then owed it to the older men started wrong to have our past mistakes corrected. To some, we explained what kind of work they could do and be very good at. That for their own good, they should look for that kind of work. Others we were able to help get going and research much better. I wanted it clear to all where they could best fit in. In this rework of our research personnel, some had to be first and some last. We had no personnel problems because of this. Each man knew that we in the management of structures research were honest and sincere and wanted to do our best by every man. I recall that once an engineer from an airplane company saying in the Washington office of the NACA, "I like the way they go about approaching the solution of a structures research problem at Langley." In general, our approach was both experimental and theoretical. Sometimes experimental tests led the way. Other times, a theoretical study led the way. It was a source of great satisfaction to me to learn that results of our research was being taught in colleges and was helping in the construction of airplanes. One day I heard a paper presented by a professor from Purdue University. He was confident something was wrong. He presented his paper in the hope that someone would show him where he was wrong. I felt sorry for this man when I heard him bluntly told where he was wrong. I thought, if it was Timoshenko who was telling him what was wrong, he would have done so with a gentle kindness that would have been admirable. So I thought, what can I say to that author that is honest and sincere, that would make him feel good? I decided to approach him after the session and say, "I have heard you present a number of papers, and I always admired you. I would be honored if you would give me the names of some of your best students so that we could employ them for structures research at Langley." He gave me the names of two outstanding men that we employed, one of whom has already addressed you, John M. Hedgepath. John Hobolt, who also has addressed you, was another of our carefully selected men who came from a different college. The employment of carefully selected and promising research men alone is not sufficient to have an excellent research staff that does excellent work. The research climate needs to be good. It needs to cause the men to grow and develop, not just get a job done. It needs to have the men be able to see clearly that their own growth as research scientists is more important than pay or position on an organization chart. If you wish to know what the structures research environment was like while I was in charge of structures research here at Langley, you might consult my paper, The Graduate School of Experience, a copy of which should be on file here at Langley. It presents not my ideas alone, but the best ideas I could assemble from our entire structures research staff. The problem of achieving well-written papers reporting the results of research was always a problem. I had great difficulty passing my courses in English composition, both in high school and in college. When I started writing research papers here at Langley Field, I found that I had to struggle long and hard. With time and patience and help from an editorial office here at Langley, I slowly learned to be able to write more easily. I was author or co-author on about 40 or more papers, and I assisted in the drafting of 50 to 100 other papers, where I chose not to let my name appear as an author. I did not want any man working under me to feel that I was trying to take credit for what he did. My job was to see that good work was done and effectively and clearly reported, and that new men grew and developed so that more difficult problems could be tackled. I developed what I called my 3 R's of research and report writing, and I'm glad that John Hobolt still remembers them. They are, I phrase them a little different from John. Make very clear what the problem is. Politicians make statements to confuse people, so stating the problem alone is not enough. You should make it very clear what the problem is. Make very clear what was done to solve the problem. Then make very clear what was learned in the effort to solve the problem, its significance if not clearly implied, and what is suggested for future research if such be the case. In the conduct of research and reporting of research results, these 3 R's must be applied over and over again to the job as a whole and to each subpart of the job or paper reporting it. I became such a hard critic of research report writing that once Dr. Batdorf told me later that he did not dare to let one of his best men sit down alone with me to read his paper. He was afraid that the man would get so mad he would hit me. That man made such remarkable development under my criticism, and his writing became so perfect that people later commented on it. Several years later, his judgment and his development and good judgment was such that for 1 year I asked him to act as division chief and make the tough decisions. I would make only the easy decisions. That way I could learn from him. Bernard Budiansky came to us at age 19. Dr. Batdorf gave him a very good problem. We were so pleased with his results and their importance, I wanted to be extra sure that his report was well written. As I read the report, I would tell Bernie how he could do better. He always caught my idea and came back immediately with an idea better than mine. Bernard Budiansky became a mature man on that first research job and the first report he wrote. I never could tell him how he could improve his later papers. He wrote them so well. While I was a hard critic of the reports written by others, I wanted hard criticism of my own work. I therefore asked John Dubert, who is now retired and associated with George Washington University here on the Langley field, to go over this talk with me. Naturally, we reminisced. He asked if I remembered the train ride the two of us took together so that we could discuss a particular research problem for a whole day without being interrupted. I remembered. Then I asked him if he remembered that several days later, when he presented his solution to the problem, Paul Kuhn stood up and said, "I can now go to the library and throw every paper on that subject into the wastebasket." Duberg had forgotten that. Of all the men in authority over me, I felt closest to Dr. George W. Lewis, the Director of Research for the NACA, whose office was in Washington. He was the only man in authority over me who would talk with me about what we were doing and how we operated in structures research. Both he and the chairman of the National Advisory Committee for Aeronautics encouraged me to continue working as we did, where we had no formal organization but emphasized the development of brain power, where research problems are selected to aid the development of men, both supervisors and new men, the men under them. About 1950, a good friend of mine in another research division on Langley Field, whose personality made him welcome in all circles and whose ambition gave nobody any worry, told me that we in the Structures Research Division were doing more to formulate the policy for all Langley Field than management itself was doing. I judge that it was our emphasis on the building of brain power that ultimately led to the George Washington University activities here on Langley Field today. In those early days, we recommended that our best men take leave and go back to college for advanced training at their own expense. In the past, when I gave a talk or wrote a technical paper or helped someone else do so, I always wanted to make sure that something new was said or reported that might be of interest to others. I will now share with you an interesting observation I made in the field of physics. It is only an observation. All the physical quantities are expressed in the CGS system of units. Because the electrical force between charges and the gravitational force between masses both obey the inverse square law, the charge on the electron, a basic physical constant, must be related to the gravitational constant, also a basic physical constant. More than one non-dimensional number exists that makes this connection through the velocity of light. The one number that I will discuss today is where K is defined by the equation, the charge of the electron is a constant times the unit charge. F1 is the unit force, C the velocity of light, and G the gravitational constant. The charge on the electron, hence K, and the velocity of light are known to a high degree of accuracy compared with the accuracy of G. Therefore, the errors in G will be the major contributors to the error in this non-dimensional constant. Rather than take someone else's recommended value for G, I decided to look at the raw test data for G published in 3 papers prepared at the National Bureau of Standards and published in 1930, 42, and 82. These data are presented in graphic form on this slide. The horizontal scale is a greatly enlarged scale of the value of the gravitational G, the numbers 6.66 and so on. The range of values for G in each series of tests is shown by the arrows, with the average value for each series indicated. There is less scatter in the values of G in each series as the experimental techniques were perfected from 1930 to 42 to 82. Also are included the values of G that correspond to 3 values of that non-dimensional constant: 896.1, 896, and 895.9. Dr. Barry N. Taylor of the National Bureau of Standards regards this 1982 series as the best, and I agree. In their 1982 paper, Luther and Toller mentioned that the test apparatus is being rebuilt to improve accuracy. Many other experimental determinations of G have been made down through the years. If plotted on this chart, they would lie some to the right and some to the left of the line marked 896. No 2 values ever agreed. There are, however, 40 experimental determinations of G made in France and reported by Ponticus in 1969 that I have plotted on this slide with the Bureau of Standards data. I've done this because the range of scatter from the highest to the lowest experimental G was only 5% greater than the range from the highest to the lowest G for the 6 determinations of G in the 1982 Bureau of Standards tests. It should be clear from this chart that the selection of a value of G must be a matter of judgment as to how much weight should be given to whose data. I therefore ask the question, can it be that nature has willed the non-dimensional constant to be 896 precisely? The test data for G, I have no basis for believing that the non-dimensional constant is 896 precisely. The Ponticus data suggests that it might be. There is also another fact that causes me to speculate that maybe it is 896. 896 is a most unusual number. Acceptance of this number makes it possible after a to obtain a calculated value for the less accurately known gravitational constant from the highly accurate values of the charge on the electron and the velocity of light, as shown on this slide. The values of K and C shown on the slide were computed from values for the charge on the electron and the velocity of light quoted to me on the phone in a different system of units by Dr. Barry of the National Bureau of Standards on September 5th this year. I use the CGS system in my notes. The equation for G on this slide must be regarded as an empirical equation that is good only in the CGS system of units. I found it just in order to satisfy my curiosity that the gravitational constant must be related to the charge on the electron through the velocity of light. Again, I have no basis for believing that the non-dimensional constant is 896 precisely. Interesting as it may be that 896 is equal to 7 times 2 to the 7th power. In order to give the average value for G obtained in the excellent data of the Bureau of Standards 1982 tests, the 896 in this equation would need to be replaced by 895.9448. I might say that I'm sure that it's more of a coincidence than anything else, but at least it gave me it was just satisfying my own curiosity. In this talk, I have only touched upon critical turning points in my life, from a boy in agriculture, then to bridge building, aerodynamics, structures research, personnel recruitment and development, report writing, and finally a little curiosity in physics. I have omitted all reference to the scores of specific structures problems that I had a part in helping solve. In each of them, as at the turning points in my life, there was a question that needed to be answered. Each time I changed my field of study, I could find a question that should be answered. The asking and answering of questions is the very essence of research. It all started for me with a question: why did one lamb in the flock have a long tail? Plus an uneducated but observing father who had more wisdom and good sense than his son when the son thought he knew it all. That's all. Afraid it would fall on him. The cow was in such misery. I showed him where to punch a hole to let the gas in the stomach escape. With a butcher knife, he was able to relieve the gas pressure and the cow lived. By the time I had finished the 8th grade, I knew it all. I was not going to high school. I told all my relatives in the presence of my father that I was not going to high school. My father said nothing. On the morning to start school, my father finished his breakfast, then said, "Eugene, go and get ready to go to school." I did as father directed. My father had had very little formal schooling, but he realized the importance of it. Having an intense interest in agriculture, half of my first 2 years in high school was devoted to the study of agriculture. In addition, I studied algebra and English in the first year, plane geometry and English the second year. I enjoyed plane geometry very much. In the summer between my second and third year of high school, I took sick. Not sick enough to be taken to a doctor, but lacking in strength so much that I could not work on the farm. So I read books that my older brother had brought home from college. One was on agricultural engineering. What I read in that book, plus my and see which gives us the larger harvest of corn. We learned that the disc cultivators was the better. My father was an observing man. He would look somewhere and say, "Do you see what I see?" Of course I did not. He would then tell me what he saw and his interpretation of what he saw. Once in the spring of 1919, he observed a field that had been in corn the year before. He pointed out alternate strips of grass and no grass, that he had cultivated where there was no grass, I where there was grass. He said that I, 10 years old, was not strong enough to push the shovels of the cultivator in deep and destroy the grass. I took my 7th and 8th grades in a rural one-room school where one teacher taught all 8 grades. At times it was 20 below zero as we older pupils helped her build the fire. There I enjoyed arithmetic and geography. As I look back on my life, I see where curiosity and a desire for understanding are essential qualities that a research man should have, in addition to honesty, patience, and a willingness to work long and hard. My first strong desire Well, I've made all the mistakes that a man can make in the stock market except to go broke. you have to foresee the future with a high degree of probability of being correct, and then you have success in your hand. But we'll not go into that subject. I haven't looked at the stock market for about 2 months as I worried about this talk. When I was verbally asked to be on this program, I was told that a summary of research I did was not wanted. What was wanted was how my brain functioned as a research man and how structures research came into being here at Langley Field. We Americans are a people with different backgrounds. I was born on a farm in northeast Nebraska. I recall our move to a small town when 2½ years old. I attended the first 6 grades in the village school, where one teacher taught 2 grades, and where the most revered and highly respected teacher flogged the bad boys herself instead of sending them to the principal. My brother, 10 years older than I, was the model boy that I wanted to be like. He was always honest, kind, helpful, patient, and did not do the unkind things that other boys sometimes do. The continuously happy part of my life began in May of 1918. My older brother was in the Army. My father could find nobody to work the farm, so our family moved from a modern house with electricity and indoor plumbing to the farm where these did not exist. Every day I worked with my father doing a man's work as best a 10-year-old boy could. My father gave me my first lesson in research. One day he said, "We will use the shovel cultivators for the first half day, then change to the disc cultivators." To learn came during the influenza epidemic of 1918. Schools were closed. We had over 2,000 lambs that had been purchased from the western ranges. One lamb had a long tail. All others had short tails. My younger brother and I were fascinated by that lamb with the long tail. We would talk about it, always look for it, catch it, hug it. That lamb was our favorite. One Sunday afternoon, my father called to my younger brother and me, "Come here, I'll show you what happens to the lamb's tails." He had found a book that my older brother had brought back from college. It showed a lamb's tail being cut off and told why. I was fascinated by that book. I read it many times. When I saw a sick lamb, I would tell my father what to do. We set up a sheep hospital. About half of the sick sheep recovered, so our death loss was cut in half. That book also told how to prevent lambs from getting sick. So we reduced the hospital admissions. My interest in the farm animals became so great that I also studied books on cattle and hogs. One day a cow was so bloated that my father hesitated to milk it. He was